Good morning, students. Welcome to the online video lecture on the new model, that is queuing model. Okay. In the previous video lecture that you had discussed the network analysis per CPM. Okay. Now that is queuing model. It is also one of the operational research technique in order to reduce the queuing. Okay, where you are, that is we are going to face the problem of queue and as well as traffic. Okay, all these factors comes under that is queuing model. Okay, how we are going to solve this queuing problem? Okay, that we are going to discuss in this chapter. It is also one of the OR technique. Okay, as you know that the queuing theory, or the we can call it as another name is waiting line theory, owes the development to the AK Erlang. Okay, he find out this technique in the 1903, took up a problem on functions of telephonic traffic. Okay, as you discussed in the introduction part. Okay, in order to reduce the waiting problem in every fields. Okay, for that one he developed the queuing theory. Here the telephonic operators were unable to handle the calls that moment they were made. Okay, resulting in the delayed calls. So that in order to make to solve the customer's problem, he find out the queuing theory. Okay, it was only after the World War II that this early work has extended to the other general problems involving the queues or waiting lines. Waiting lines problems are either because the first one is there is too much demand on all facilities, so that we say that there is an excess of waiting time and inadequate number of service facilities. And second one is there is too less demand, in which there is too much idle facility time to many idle time, sorry, too many facilities. In either case, the problem is to either schedule the arrivals or provide the proper number of facilities, or the both, so as to obtain an optimum balance between the costs associated with the waiting time and idle time. In operational research can quite effectively analyze such queuing or congestion phenomena. However, a sound understanding a queuing theory combined with the imagination is required to apply the theory to the practical situations. Now these are the characteristics of the queuing problem. The first one is units arrive at a regular or irregular intervals of time at a given point called as service center. Okay, for example, the truck arriving a loading station, customers entering the department store, persons arriving in cinema hall, ships arriving at port, wherever the traffic, wherever the waiting situation that you are going to occurs in many day to day life. Okay, and second one is one or more service channels or service stations or service facilities, okay, are assembled at the service center. If the service station is empty, is the arriving customers will be served immediately. If not arriving, customers will wait in a line till the service is provided. Once service has been completed, the customers leaves the system. Whenever the customers coming to a service facility in a such a way that either the customer or facility has to wait. Okay, the major constituents of the queuing system is, the first one is, as you know, that customer arriving unit that requires some services to be performed, as already described. Queue means the number of customers waiting to be serviced. Okay, that queue is not included the customers currently being serviced. Service channel, the process of or facility which is performed the services to the customer. This may be single or multi-channel. This is very important. This may be single or multi-channel. The number of services channel denoted by the symbol C. Next, elements of queuing system, structure and queuing system. The first one is input or arrival, or we can call it as inter-arrival distribution. Second one is output or departure service distribution. Third one is service channels. Fourth one is service discipline. Fifth one is maximum number customers are allowed in the system. Next, sixth one is calling source or population. Seventh one is customer behavior. Next one is operating characteristics. Operating characteristics are, the first one is, that is queuing length. The queuing length means the average number of the customers in a queue waiting to get the service. Okay, that is denoted by LQ. Next, system length, that is denoted by LS, the average number of the customers in the system including those waiting as well as those being served. And third one, that is waiting time, that is WQ, the average time of for the which the customer has to wait in the queue to get the service. Next, fourth one is the total time in the system, that is the average total time spent by the customer in the system from the moment he arrives till he leaves the system. It is taken to the waiting time plus the service time. Fifth one is utilization factor, that is denoted by rho. It is the proportion of time to the server actually spent with the customers. It is also called as traffic intensity. Now, the formula, that is waiting time and idle time cost. Okay, that is CW expected waiting cost, LS is expected number of units in the system, CF cost of servicing the one unit. Okay, then expected waiting cost per unit time, that is CW into LS, that is given by CW into lambda divided by mu minus lambda. Okay, expected service cost per unit time period is CF minus mu, that is total cost equals to C equals to CW into lambda minus mu minus lambda plus mu into CF. This is the minimum if D differentiate, that is with respect to mu, d by d mu, that is C equals to 0. Okay, the final, that is which is mu, is given by lambda plus or minus under the square root of CW divided by CF into lambda. Note that here the plus and minus are appear before the square root sign. Okay, negative value of mu is not possible answer in real life problems. Okay, the negative sign indicates if it is mu is given by the above the equation called, that is minimum cost service rate. Okay, here the plus and minus sign is very important. The minus sign that indicates the answer, or whatever the answer we are getting, it is not possible, and in the real life positive that indicates it is possible. Now here there is a small explanatory on the formulas, queuing formulas. Okay, the traffic intensity, the ratio, that is lambda by mu, is called as traffic intensity. Okay, it is determines the degree to which the capacity of the service station is utilized. Okay, for instance, if customers arrives at the rate of 9 per hour and the service rate is 10 per hour, the utilization of the service facility is 9 by 10, that is 90%. And next is, that is second, average length of the queue, that is lambda by mu into lambda by mu minus lambda. Consider that statistician observe that queues at a service facility after every 1 hour, and that length of the queue for say 6 observations is as follows. Observations are 1 to 6, queue none, that is in the third you are getting none, and service facilities also, that is going to star mark, that is length of the queue is here we are getting at the 2, average is, that is 12 by 6, that will gives the 2. Now average number of units. Okay, average number of units in the system, it is lambda by mu minus lambda. For the above is situation, this you can write, that is lambda 0 plus 0 mu minus 0, that is 6. average length of the non-empty queue, that is lambda by mu minus lambda. Okay, this will be calculated observations from 2, 4, 5, 6. Okay, and 1 and 3 queue was empty. Through the during observation there was a unit being served. For the above situation, then this is the average. Okay, 2 plus 5 plus 2 plus 3 divided by 4, that is equals to 3. Now the fifth one is average waiting time of an interval lambda divided by mu divided into mu minus lambda. Okay, that you are getting. Okay, the average waiting time. Okay, add all the times divided by 8, 41 by 8, that will give 5.2125. And next one is sixth one is average waiting time of an arrival who waits 1 divided by mu minus lambda. In the above situation, ignoring all the observation, when the waiting time is 0, that you are getting 41.6, that will gives us 6.83 minutes. Next, the seventh one is average time an arrival spent in the system is, that is 1 divided by mu minus lambda. Here that will gives the formula is total into waiting time plus service time divided by 8. Now go to the first example here. He has given a self-service store employs one cashier as its counter. 9 counters arrive in average minutes, while the cashier can serve the 10 customers in 5 minutes. Assuming the poison assuming the Poisson distribution for arrival rate and exponential distribution for the service time. Find. Here you need to find the average number of customers in the system. Second one is average number of customers in the queue or average queue length. Third one is average time or customer spends in the system. And fourth one is average time a customer waits before being served. Now the solution is arrival rate, that is lambda equals to 9 by 5. Okay, 1 by 8 customers, and service rate mu is given 10 by 5, that will gives 2. Next, go to the formula, that is average number of customers in the system, that is ls is given by lambda minus mu minus lambda 1 by 8 divided by 2 minus 1 by 1.8, that will gives 9. Next, second one is average number of the customers in the queue, that is LQ divided, that is equals to lambda square minus divided by mu into mu minus lambda, that is will get the 1.8 divided by 2 into 1.8 divided by 2 minus 1.8, that will gives 8 by 1. Next, third one is average time of a customer spends in the system, that is WS 1 divided by mu minus lambda, that is 1 divided by 2 minus 1 by 8, that is equals to 5 minutes. Next, average time a customer waits in the queue, WQ, that is lambda by mu equals to 1 divided by mu minus lambda 1 by 8 divided by 2, 1 into 1 by divided by 2 minus 1 by 8, that will gives 4 by 4.5 minutes. Okay, now similarly go for second example here. A shipping company has a single unloading dock with the ships arriving in a Poisson fashion at an average rate of 3 per day. The unloading day distribution for a ship with an unloading crew is found to be exponential with the average unloading time 1 by 2n days. The company has a larger labor supply without regular working hours, and to avoid the long waiting times, the company has a policy of using as many unloading crews as there are ships waiting in line or being unloaded. Okay, the first one is the average number of unloading crews working at any time, and B1 is the probability that more than 4 crews will be needed. Here he has given, that is lambda equals to 3 ships per day and mu n equals to n into mu. Average unloading time with n crews, that is 1 by 2n days, and the average of unloading time with one crew is, that is 1 by 2 day. in order to, that is, mean of unloading the rate with one crew, that is mu equals to 2 ships per day. Now we need to calculate the expected number of unloading crews. Okay, that we have, that is ls equals to summation, that is raised to infinity to the n equals to 0. Okay, that is npn. Okay, now we can apply the formula here. Okay, that is the summation of raised to, that is infinity to n equals to 0 to n into p raised to n divided by n, that is e raised to minus p. Okay, we can write like this: e raised to minus rho, that is 0 plus rho plus 2 by 2 summation p square rho square plus 3 summation, that is p rho 3, sorry, rho raised to rho cube plus, that is go for infinity. Okay, now that is e raised to, that is minus rho into rho, that is 1 plus rho square divided by 2 plus, that is goes on infinity. Okay, that will gives the e raised to minus rho minus into rho into e raised to rho, that we are getting lambda by mu equals to, that is 3 by 2, that is equals to 1 by 5, that more than 4 crews will be needed here. Okay, next, second B, we need to find out the probabilities that more than 4 crews will be needed. Okay, how we are going to find out that one means, the probability that more than 4 crews will be needed, that is probability there are at least 5 ships in the system. Okay, that we have got here, that is pn minus pn. One is from infinity to n equals to 0 and minus, that is summation of from 4 to n equals to 0, that you are getting 1 minus, that is write on p naught plus p1 plus p2 p3 p4, and that you are getting equals to 1 minus e raised to minus rho, that is 1 plus rho square minus 2 1 plus rho cube by 3 plus rho 4 divided by 4i equals to, that is rho n equals to, that is rho n minus e raised to minus rho divided by n. Okay, here we are getting equals to 1 minus e raised to minus 1.5. Okay, here the summation is that is into 1 plus 1 minus 5, 1 plus 1.5 plus 1.5 square divided by 2 summation plus 1.5 q divided by 3 plus 1.5 raised to 4 divided by 4, that we are getting 0.19. Now coming to the MMC model that is multi-channel system can be found out here. Expected average number of customers in the system is, that is given by, okay, that is star ls, that is lambda into mu divided by lambda a divided by mu raised to c divided by c minus 1 into c mu minus lambda square p naught plus lambda divided by mu. Next, expected average number of customers waiting in the queue, LQ minus LS minus average number of being served, that is given by lambda mu divided into lambda by mu raised to c divided by c minus 1 into c into mu minus lambda whole square into p naught. Next is the third one is average time a customer spends in the system, that is given by ws equals to ls by lambda equals to, that is mu into lambda by mu divided by c mu raised to c divided by c raised to 1 into c mu into lambda square into p naught plus 1 divided by mu. Now the fourth one is average waiting time of a customer in the queue, that is wq into l equals to lq divided by lambda equals to, that is mu divided by lambda by mu raised to c divided by c raised to 1, that is into c mu into lambda square into p naught. The probability the customer has to wait, that is p into n, that is greater than or equals to c, a equals to mu into that is lambda by mu raised to c divided by c minus 1 into c mu minus lambda into p naught. Next, the probability that the customer enters the service without waiting, that is given by 1 minus p into n raised to, that is greater than or equals to c equals to 1 minus mu into lambda divided by mu raised to c divided by c minus 1 to c mu minus lambda, that is into p naught. Next one is average number of the idle servers, that is c minus average number of customers served. Next, utilizations rate rho equals to, that is lambda divided by c into mu. Next is efficiency of the MMMC model is, that is average number of the customers served divided by total number of customers. Next, the example is a tax consulting firm has 3 counters in its office to receive the people who have the problems concerning their income, wealth and sales taxes. On the average, 48 persons arrive in an 8 hours day. Each tax advisor spends 15 minutes on an average on an arrival. If the arrivals are poisonally distributed and service times are according to the exponential distribution. Here we need to find the average number of customers in the system, average number of the customers waiting to be served. Here the problem comes under MMC. Third one is average time a customer spends in the system, average waiting time for a customer. The number of hours each week a tax advisor spends performing his jobs, the probability that a customer has to wait before he gets the service. Next, the expected number of idle tax advisor at any specified time. Now the solution go for, here it is c equals to 3, lambda equals to 48 by 8, 6 hours, mu equals to, are getting 1 by 15 into 60, that is 4 hours, lambda by mu, that is 3 by 2. Now we need to find out the p naught by using the formula 1 divided by summation of the, that is c raised to minus 1 n equals to 0, lambda by mu raised to n divided by n plus lambda by mu raised to c divided by c into c mu, that is c mu minus lambda. Okay, that we are getting p naught equals to 0.21 probability. Now the first we need to go for find out the average number of customers in the system by using the formula, that is ls equals to lambda into mu divided by lambda by mu raised to c divided by c minus 1 into c mu minus lambda whole square into p naught plus lambda by mu. That will gives 1.74. Next, go for B1, that is average number of customers waiting to be the served, that is LQ equals to LS minus lambda by mu, that is equals to 1.74 minus 3 by 2, that is 0.24. Next, C1 is average time a customer spends in the system, that is WS equals to LS divided by lambda, that is 1.74 divided by 6, that is equals to 0.29 hours, that is equals to 17.4 minutes. Next, D1 is average waiting time for a customer, that is WQ equals to LQ divided by lambda, that is we are getting 0.24 by 6, that is equals to 0.04 hours and equals to 2.4 minutes. Next, utilizations factor, okay, that is rho equals to lambda by c mu equals to c is 6 divided by 3 into 4, that will get 1 by 2. Number of hours each day a tax advisor spends doing his job is 1 by 2 into 8, that is equals to 4. And on and average a tax advisor is busy into, that is 4 into 5, that is equals to 20 hours based on 5 working day weeks. Okay, that is the probability of when a customer has to be wait, that is given by the formula is P, that is n greater than or equals to c, that is given by mu into lambda by mu into raised to c, c minus 1 into c mu into lambda into p naught, that you are getting 0.236. okay, next go for that is G1. We know that probability of no customer in the system is P naught, which means that all the three tax advisors are idle. We have to determine P1 and P2 probability, that is two tax advisors and one tax advisor respectively are idle. okay, for one, that is P raised to n equals to 1 by n, that is lambda by mu raised to n, where is n is less than c, so that we can apply, that is P raised to 1, we are getting 0.315. similarly do it for P2. okay, 1 by 2 into 3 by 2 raised to 2 into 0.21, that we are getting 0.236. next, it is expected number of the idle advisors at any specified time is, that is equals to 3 P naught plus 2 P1 plus 1 P2. okay, substitute P1, P2, P3 values, that we are getting 1.496 and it is randomly equals to the 1.5. alternately utilization factor, that is lambda by c divided by mu equals to, that is 6 divided by 3 into 4, that we are getting 1 by 2. Thus the each tax advisor is busy for half the time and hence also free for half the time. expected number of the idle tax advisor is 1 by 2 into 3 equals to 1.5. okay, this is regarding the queuing theory. okay, in this model that you had discussed the network analysis, that is PERT and CPM. next is queuing model. The one question is coming from project evaluation reveal technique and critical path method, and for the 16 marks questions, and another 16 marks questions is coming from queuing theory. We can solve from PERT CPM or we can solve from queuing theory. okay, thank you.